So welcome all. Welcome to the Physics Colloquium series. Welcome all. Welcome to the Physics Colloquium series of spring semester 2021. I will be in charge of this colloquia. I just want to stress that we will go on with the format of the previous semester. Every 2 weeks, we have Israel Physical Society Colloquium fully online. And hopefully, every alternate week, we have like some sort of hybrid colloquium as we will hold today in this room and on Zoom. So that will be advertised by email as usual. So I would like to start and invite our speaker today, Yosi Avron, who kindly agreed to give a talk in memory of Nathan Rosen, who passed away 25 years ago. And I also would like to welcome Nathan Rosen's family, who is online with us today. Maybe let me say one thing about Yosi and Nathan Rosen. So Yosi actually took physics classes with Nathan Rosen, in classical mechanics, theory of elasticity, general relativity. But today will tell us about another very interesting aspect of physics, which is entanglement. So Yosi, the stage is yours. Thank you.
Thank you, Vincent. Good. It's really a wonderful pleasure to see all my friends again after this terrible year with this corona. So I want to tell you, I want to give a mixed colloquium, which will be partly history, partly science. It will be about Nathan Rosen, who founded this department, and I'll talk about his life and his science. And I'll try to entangle this story about his life and science with the story of entanglement, which first appeared in a joint paper of Nathan Rosen with Albert Einstein and Boris Podolsky. Nathan Rosen was born at the beginning of the 20th century, 1909, and he died at the end of the 20th century, 1995, December. So his life really overlapped with the 20th century, which was an eventful century. There were 2 world wars. There was the Bolshevik Revolution, and there was the creation of the State of Israel. And all these cataclysmic events are weaved in the story of his life, and I'll try to outline some of these things. As a leitmotif, or as about of this lecture, will be the story of the most cited paper, not of Nathan Rosen, but of Albert Einstein. So the most cited paper of Einstein, which is a joint paper with Nathan Rosen and Boris Podolsky, known to everybody in this audience as the EPR paper, is the most cited paper of Einstein. And if you check, I checked in Google Scholar, and it is cited about 30,000 times. I think it is also the most cited paper in physics. And it is an unusual paper, and it's actually a little surprising.
It's not the most cited paper.
Okay, yours is.
No, of Einstein, it's not the most.
It is. Okay. So this is what Google says. I trust Google Scholar. And actually, there is a good reason why this is the most cited paper of Einstein, and not, say, his general theory of relativity or special relativity theory of relativity, or the photoelectric effect or Brownian motion. And I'll get to it. And I think the reason is twofold. First of all, because these other works of Einstein were more or less immediately accepted, and they were transferred more or less immediately into textbooks. But this was controversial for 50 years. Now, the paper is unusual in more than one respect. If you look at the title doesn't sound like a title of a paper in physics, but rather like a title of a paper in philosophy. Read the title: Can quantum mechanical description of physical reality be considered complete? This sounds like a question not in physics, but rather like a question in metaphysics. As we shall see, the evolution of this paper was really miraculous and wonderful. It started as a paper in metaphysics, and it laid the foundation to something which is extremely practical and concrete. So today, many people are interested in the quantum revolution, quantum computing, quantum sensing, quantum cryptography, and all these new development in physics rest on a resource which was invented in this paper of EPR, which is entanglement. So it started as a paper, it started as an issue of what is physical reality. Once the paper appeared, by the way, Schrödinger read the paper and wrote in German to Albert Einstein a letter where he coined the term entanglement. The term entanglement did not exist, and you cannot find it in the EPR paper, but it grew out of this EPR paper. And today it is viewed by many people as a technological resource, entanglement. And I think this line of development, which took many years, is one of the reasons that the paper is really so highly cited. It is cited today, of course, much more than it was cited 50 years ago. Okay, so let me start at the beginning. As I said, Nathan Rosen was born in 1909. When he was 6, I think the First World War broke out. And when he was 10, the world was struck with this Spanish flu. And the picture in the middle of the figure, this is a picture of a funeral in New York during the time of this Spanish flu. On the right, you see a picture of the young Nathan Rosen, and I owe this picture to Joe Rosen, his son, who was a professor of physics in Tel Aviv University and who helped me with various aspects preparing this talk. When Nathan Rosen was 20, the Great Depression hit America, and this I show in the picture on the right. So his youth was tumultuous. So Nathan Rosen went to MIT, and where he did both his bachelor and his PhD under the supervision of John Slater. I think many of us know John Slater. This is the guy whose name is attached to a determinant. And Nathan Rosen wrote various papers as a graduate student at MIT, but none with John Slater. But I think John Slater had an important influence on Nathan Rosen because John Slater, of course, forced Nathan Rosen to think about quantum mechanics of many particles, not just about one particle quantum mechanics. And this is the essence of the thing that will come up later, which is the story of entanglement. among the papers he wrote as a graduate student at MIT was this paper which is cited here in the middle. It's called The Neutron. The paper was written a year before Chadwick discovered the neutron. And in this paper, Nathan Rosen proposes that it would be a wonderful thing if a neutral particle with a mass similar to the mass of the proton would exist. And he gave it the name neutron. The paper has been more or less forgotten, and it is not credited with the discovery of the neutron. I don't know if I want to go into the details, but basically the physical model that Nathan Rosen had for this neutron was a bound state of proton and electron. But now we all know that the bound state of an electron and atom makes the hydrogen atom, not the neutron. So in order to make the neutron, and of course Nathan Rosen knew this, so in order to get the neutron, so an object which is much smaller than hydrogen, he modified the Coulomb law at small distances. So because this is today viewed as a wrong model, I think the paper didn't catch, but it's a nice paper.
Who's the other author?
Let me see.
Yeah.
Langer, M. Langer. I don't know who is Mr. M. Langer. Okay. Now I want to start a new chapter, and I want to tell you the story of the founding of the Institute of Advanced Study in Princeton. On the left, you see a picture of Princeton in the 1930s. Doesn't look very inviting, I think. The Institute of Advanced Study was founded in 1930 by a generous donation of Louis Bamberger and Mrs. Fulde. Mrs. Fulde was his sister, and the two of them gave $5 million to establish an Institute of Advanced Learning. And I want to tell you a little bit about this institute, or about the mission of this institute. They appointed as the director of this institute the gentleman that you see here on the left, Abraham Flexner. Abraham Flexner was a well-known, famous educator at the time in the US. And he was credited by transforming the system of American medical schools. And because of his role as a well-known educator, the Bamberger family decided to entrust the Institute of Advanced Study to Abraham Flexner. Now, Abraham Flexner, I want to tell you something about his vision because I think it is interesting. So he wrote a paper in Atlantic which explains his vision of what the Institute should focus on and what should be the mission of the Institute of Advanced Study. And the title of the paper is The Usefulness of Useless Knowledge. I think today we call useless research blue sky research. So it's a curiosity-driven research. It's not research driven by need or by purpose. And I want to read to you a small paragraph from the paper of Atlantic. This paragraph is almost 100 years old, but certain truths remain valid even after 100 years. In a world steeped in irrational hatred, men and women, old and young, detach themselves from the angry current of daily life to devote themselves to the cultivation of beauty, to the extension of knowledge, just as though fanatics were not simultaneously engaged in spreading pain, ugliness, and suffering. Unless the world is made a better world, a fairer world, millions will die, will continue to go to their graves, silent, sad, and embittered. So, now there was an interesting coincidence that in 1933, 3 years after the Institute was established, Einstein made his third trip to the US. He made the trip at the time when Hitler rose to power in Germany. And he was in America when Hitler came to power. And so this, I think the picture of Einstein riding bike in Caltech, many of you recognize. And the Bücherverbrennung is what I thought is a nice way to depict the rise of Nazism in Germany. And shortly after Hitler came to power, he issued this famous law that essentially dismissed all the Amter, all people of Jewish origin from their position, and this included Einstein. Einstein was in America at the time, so he didn't have to think a lot whether he wants to go back to Berlin or stay in America, and he chose to stay in America. And he accepted this position of Abraham Flexner at the Institute of Advanced Study, and he started his appointment there in 1934. In 1934, Nathan Rosen was a postdoc or a young assistant professor at Princeton University. And Einstein met Nathan Rosen on campus. And they had a talk, and Einstein invited Nathan to join him as his research assistant. Einstein also invited another person to join him. This was Boris Podolsky, a relative of our Podolsky? I'm afraid not, no? No. There is actually a letter of recommendation or a letter where Einstein writes to Flexner why he wants to appoint Boris Podolsky. And he tells that he wants to appoint him because he's the most gifted man who wrote a joint paper with Paul Dirac. The two of them, Boris Podolsky and Paul Dirac, wrote a paper when both of them were in Kharkov, Russia. And we will see this theme that of people going through Russia at this period coming again and again. So in 1935, Einstein, Podolsky, and Rosen submitted this paper that I showed you before, the EPR paper, to Physical Review. And essentially, by the time that it was the authors received, the paper was apparently written by Boris Podolsky. And when the paper was about to appear, Boris Podolsky contacted the New York Times and told them about this paper. And the New York Times came with this headline: Einstein attacks quantum theory. And this was few weeks before the paper appeared. And Einstein was furious. The son of Nathan Rosen, Joe Rosen, sent me some of the letters that Einstein exchanged with, or notes that Einstein exchanged with Nathan Rosen regarding how to respond to this, to the New York Times paper. And here is shown one of them. Einstein and Rosen corresponded in German. So those of you who can read German can read the first, this section here. But these drafts of notes, that they wanted to write to the New York Times was not what eventually appeared in print. And I just want to quote one line from what appeared eventually in the letter Einstein wrote to the New York Times, which is written at the bottom, I deprecate advanced publications of any announcement in regard to such matters in the secular press. I think it's really interesting how Einstein viewed the New York Times. Now, since this is a physics colloquium, it won't be all just history. There will be also a little bit of science. So let me tell you what was this EPR. What was the argument made by Einstein, Podolsky, and Rosen? And it is based on an identity. And the identity is written, as you can see here. Can I use the pointer and show that it is written up there? Well, there's just, yeah, the identity on the top. What you see in this identity on the top? Well, on the left-hand side, you see quantum states of two particles, one of them denoted in red with the subscript A for, say, Alice, and the other one by B with subscript B for Bob. So these are two particles. On the left-hand side, the particles of Alice has momentum P, while a Bob particle has momentum minus P. And the left-hand side also tells you that there is a superposition of all particles of all momenta. So the fact that there is a superposition of all momenta means that the momentum of Alice's particle is completely unknown, and so is the momentum of Bob's particle. However, if Alice knows what her momentum, if she measures her particle and picks a certain momentum, then this forces Bob's momentum to be the opposite, because the two momenta are paired as seen in this formula. On the right-hand side, you see that the same, it's an identity. On the right-hand side, you see that the same quantum state can also be written as a superposition of particles in position. So here, Alice's particle is in position X, and Bob's particle is in position X plus L. And again, the right-hand side is a superposition where all positions are allowed. So if you look at the right-hand side, Alice has no idea what is the position of a particle. On the left-hand side, you see that Alice has no idea what is the momentum of a particle. But in either case, you see that if Alice knows her momentum, she knows what's Bob's momentum. And if Alice knows what's her position, then she knows also what Bob's particle position is. Now, EPR made the following argument. Since Alice can predict Bob's particle's position or momenta without ever touching these particles, the position and momenta of Bob's particle are elements of reality. This is what they defined as element of reality. If you can make a prediction which is absolutely sure, but without an error and without disturbing the particle. So they say if X and P are elements of reality, they do not have correspondence in quantum mechanics, and this contradicts the because it contradicts the uncertainty principle that says that the position and momentum of Bob's particle cannot be known do not have physical reality in quantum mechanics. They can't exist simultaneously. Good. So when the paper appeared, this threw Bohr into insomnia, and he responded. I think one of his colleagues described it, that the paper appeared like a bolt from the sky. And he gave his response to this argument of Einstein, Podolsky, and Rosen. And he said that this reasoning is faulty because it is based on what today we would call counterfactual reasoning. What do I mean by counterfactual reasoning? You see, Alice can decide that she wants to measure P or she wants to measure X. But once she made the decision, she made one decision. She cannot do both. Therefore, it is not true that both P and X for Alice have simultaneous physical reality. So this was the Bohr response. I think it's a fair response. And I want to say something about, there is something about this, about the Einstein-Podolsky-Rosen, people call it sometimes paradox, which is a common misunderstanding. Some people think wrongly that the Einstein-Podolsky-Rosen shows that quantum mechanics allows the transmission of information instantaneously. This is nonsense. And in fact, this is something that Nathan Rosen explained to me. I remember we walked out of this colloquium room, and when we were walking on the steps, he told me why this is a wrong interpretation of the EPR. I will not tell you what Nathan Rosen told me at the time, because I chose to put this picture, and I'll illustrate the idea with this picture. This version is, which was coined by John Bell. It was called by John Bell, Bertelsmann socks. So John Bell had this colleague of his who had this slightly idiosyncratic habit that he would wear socks of different color. Let's say that he would always wear a red sock or a green sock. Now, it was always a red sock or a green sock, but it could be red on the left or green on the right, or red on the right and green on the left. Now, if Bertelsmann's trousers were down, there's no way of you to know what color of the sock is on his right foot. But if you would lift the hose on the right foot, you would also know immediately, instantaneously, what's the color of the sock on the left foot, even if the left foot was in Andromeda. So you see from this example that the fact that if Alice measures her particle and she knows what would be the result of Bob's measurement, this does not transmit any information between Alice and Bob. It's just Alice knows something. That's it. It's this Bertelsmann stocks. Okay. Now, there are two issues with quantum mechanics that I think Einstein was not very happy with. And one issue is the fact that quantum mechanics is probabilistic. And the other issue is that the quantum mechanics has a weird notion of reality. And I think Einstein expressed it in many ways. One of the nice ways is the moon there when nobody looks? And the reason that the quantum mechanics has a weird notion of reality is because quantum mechanics differs from classical mechanics in its view of what is the role of the observer in an observation. In classical mechanics, observations reveal. There is a pre-existing reality which an observation just reveals. America was there before Columbus discovered it. In quantum mechanics, observations do not reveal. In quantum mechanics, observation prepare. If you observe the particle to have a certain momentum, you prepared it at this moment so that it has momentum, given momentum later. But it does not say that it had this momentum before. So I think there is a nice picture that I learned from Jörg Fröhlich, which tries to describe this view of evolution in quantum mechanics as a tree of diminishing potentialities. You can also view it as a philosophical outlook on life. So you start at the root of the tree, and every measurement allows possible distinct consequences. But once the measurement is performed, you picked one branch of the tree. And then you walk along the tree, and whereas previously at the root you had this multitude of potentialities, as time goes on, the potentialities shrink on you. You pick the path. Now, I put the two trees here just to illustrate that in the case that Alice and Bob are entangled, there is a correlation between the path that they take. So if Alice picks a certain path, this forces a certain path on Bob, at least initially. Okay. Good. Now, the Einstein and Bohr corresponded on this issue of reality and randomness in quantum mechanics for several years. And let me read some quotes. Here it is. Here is Einstein quote: "I, at any rate, am convinced that he, God, does not throw dice," to which Bohr reported, "Einstein, stop telling God what to do." Here is a picture of Bohr with Pauli, and Pauli thought that Bohr's argument with Einstein focused on the wrong thing. As I said, there were two issues, contentious issues. What's the notion of reality? And the other one is randomness. And so Pauli at one point said to Bohr, you had erected some dummy Einstein for yourself, which you then knocked down with great pomp. People were more direct, I think, in those days than they are today. Now, I think this weird notion of reality of quantum mechanics has led to lingering uneasiness that has not dissipated, that is still with us today. So there are many famous quotes associated with this uneasiness. David Mermin said, characterized quantum mechanics in this phrase of shut up and calculate. Richard Feynman said that nobody understands quantum mechanics. Do you want to know in what context he said it? It's a little interesting. Anybody cares?
We all care.
You all care.
I remember a quote about, I think they said that a few people understand general relativity.
Yeah. So let me continue what you just said. Einstein said that you often read that there are only 5 people in the world who understand general relativity. And then Feynman said, I think there was no period in time in history when 5 people understood general relativity. There was a period when nobody understood. There was a period when just one person understood. And when he understood it, lots of people understood it. But in contrast, I can guarantee you that nobody understands quantum mechanics. Asher Perez wrote a lovely article in Physics Today where he said quantum mechanics needs no interpretation.
What's his name?
David Mermin. And Einstein, Schrödinger made a rather remarkable statement, you know. I don't like it. I'm sorry I had anything to do with it. And my friend Asa said to me, there is no reality, there are only correlations. So I think this EPR paper entered into the pantheon of physics. There is another notion of that went into the pantheon of physics associated with Einstein and Rosen, and this is the Einstein-Rosen bridge. The Einstein-Rosen bridge appears in this paper, which I show here, the particle problem in general theory of relativity. It's a lovely particle. It's a lovely article, although I think most people would say that it is wrong. But in this particle, they proposed the notion. They studied the Schwarzschild solution of in general relativity of black hole, and they considered the singularity in this in the Schwarzschild model, and they proposed that the singularity could serve as a bridge between distinct worlds. And this caught on also in the science fiction literature. It is sometimes called the wormhole, or sometimes and physicists call it the Einstein-Rosen bridge. And here is a picture of an Einstein-Rosen bridge, which is this wormhole that connects distinct worlds. This paper was actually written by Nathan Rosen, and you would be pleased to know that the original draft of the original draft before being typed of this paper exists at the archive of the Technion. So here is a picture of this. This was with the handwriting of Nathan Rosen. Okay, now once Nathan Rosen finished his tenure with Einstein, he slightly later, 2 years later, he took a position in Kiev, and he stayed in Kiev from 1937 to 1939. He moved with his family. He was married at the time, and his first son, Joe, was born in Kiev. And I find it, I don't know why Nathan Rosen chose to go to Russia. I think he had serious interests in socialism or communism, and it is actually quite likely that he was a communist himself, and he wanted to try out the communist way of life. Perhaps he was also an adventurer, I don't know. And perhaps also that, this time this time in America was flooded by all these scientists who escaped Europe. So perhaps it was also difficult to get a position in the States. Anyway, he secured a temporary position at the University of Kiev for 2 years. And to secure this position, it is really, today it is unheard of. Einstein wrote a letter to the Secretary General of the Communist Party, Mr. Molotov, asking him to give a position to Nathan Rosen. Anyway, apparently the 2 years in Kiev were not very happy years. I think the family decided after 1 year that they had enough of this Russian experience, and they moved back to the States. And a year later, Nathan Rosen joined them. And after a short while, he got a position in Chapel Hill, where he stayed from 1941 to 1952. Now, in 1952, he got an offer from the Technion. So let me say something about the Technion for the young members of our department who may not know the full history of this institute. So the Technion, which was founded in the 20s by a German charity organization called Hilfe, had this beautiful building in Hadar, and until the 1950s, it was actually a Fachhochschule, you know, a school for technicians. It wasn't really a university, and in fact, Einstein objected that it would be a university. He thought that Palestine needs technicians, not professors. But in 1950s, the Technion got the president. The Technion appointed as its president Dori, who was Yaakov Dori, who was the first chief of staff of the Israeli army. And Dori decided to transform the Technion from a technical school to a full-fledged university. And he decided that there should be a physics department run by a major scientist. And he solicited Natan Rosen. Natan Rosen first came on his own. The family stayed in the States. And after a year, he went back to the States to bring the family. And Joe told me that on the way from, Joe is the son of Natan Rosen, on the way from Chapel Hill to Haifa, they stopped at Princeton to say hello to the big man, Mr. Einstein. So here I collected 4 pictures. One of them is a letter, which is amusing. You will find it at the, I think on the physics faculty website. Shall I read it for you or just tell you what's written here? It's a letter written by the president of the Technion to the chief engineer of the post office, asking him if it is possible to install a telephone line at the house of the head of the physics department at the Technion. So anybody can guess what's the answer he got? Forget it. No. So this was the Technion in the 50s. This is a picture I saw of graduate students. Perhaps Yoshua or Micha can recognize. I recognize one person here, which is Gidon Erez. Gidon Erez did his master's with Natan Rosen at the time, but it is interesting that the students at the time came to the Technion with jackets like it should be. So I think the arrival of Natan Rosen to the Technion was a tremendous boost, and he, among other things, recruited major scientists to the Technion. I mentioned just one of them, David Bohm. It's also the Bohm story is also an amazing story. Bohm was an American. He was an assistant professor at the University of Princeton, and he was a communist. And during the McCarthy era, he was subpoenaed to testify in front of this McCarthy or some kind of a committee, and he was asked to snitch on his communist friends, which he refused. And then his American citizenship was revoked. There is another crazy story about David Bohm, which is unbelievable. When David Bohm wrote his thesis, the thesis was more or less, this was during the Second World War, the thesis was more or less immediately classified, and he was not allowed to see it anymore. Robert Oppenheimer, he got his PhD because Robert Oppenheimer wrote a letter to the university attesting that the gentleman wrote a thesis. So this is the story of David Bohm, who arrived at the Technion. And at the Technion, David Bohm met a student, Aharonov, and both of them, by the way, both of them wrote a paper, their version of the EPR paper, which is much more popular when we teach the EPR paradox, because they moved from continuous variables to spin. And at the Technion at the time, there were, and then David Bohm and Aharonov moved to Bristol. David Bohm stayed at the Technion very short period. Then they moved to Bristol, where they made together this famous paper, which we all know, the Aharonov-Bohm effect. At the time, there were the two students at the Technion in the late 50s, were Asher Perez, who did his PhD with Nathan Rosen on gravitational waves, radiation of gravitational waves, and Yoshua Zak, who is present here, who did not do general relativity. He did group theory. And if I remember something about non-symmetric groups, correct, Yoshua? I hope so. Yoshua had the co-advisor, which was Yoel Rakach at the Hebrew University, but his formal advisor at the Technion was Nathan Rosen. So these are two students of graduate students of Nathan Rosen. There is an amusing pamphlet which Uri Sivan brought to my attention. This is a public lecture of, you see, Professor David Bohm, the Technion, and the title of this, the title of the lecture which he gave is, in English, it is Philosophical Problems of Quantum Mechanics in the Light of Dialectical Materialism, and in Hebrew, בעיות פילוסופיות של מכניקה הקוונטים לאור המטריאליזם הדיאלקטי. And I think the funniest thing is, to whom was this lecture delivered? The lecture was delivered חוג הפיזיקאים המרקסיסטים בית הקיבוץ הארצי. Unbelievable, right? Now, in the 60s, the Technion campus moved from Neve Shaanan to where it is, from Hadar to Neve Shaanan. And here is a picture of Nathan Rosen, I think with the donors. I think that this was also the Rosen family, but it's a different Rosen, looking at the plans for the construction of this, of this part of the building. And I added here a picture of the what we now know as the H-Bar Cafe, the tea room in physics in the 60s. I don't know if you can whom you can recognize in this picture. Shall we make a test? Do you know who this gentleman is? See, the first one. This say the one on the right. No, this is Baruch Rosner. This is Yoshua Feldsteiner. This is Baruch Zinger. And who is this beautiful woman? Bertina Fischer, right? And who is this young lad? Right? Okay. Now, in the 60s, I think in the late 60s, Nathan Rosen also was instrumental in building the School of Engineering of Ben-Gurion University. And as a way of recognition, in Be'er Sheva, there is a major boulevard, which is called the Nathan Rosen Boulevard. When I was a chairman of the physics department, I wrote to the mayor of Haifa, Yona Yahav, with a request that they name a street in Haifa after Nathan Rosen. And I got a nice letter response that the Vadat Hashemot, the committee for naming streets, considered this request, and unfortunately, it was turned down. Why? Because Haifa has a Natan Street and has a Rosen Street. And if you would add another Natan Rosen, people would just get lost everywhere. So they had I want to close by getting back to doing something physics so that it would not be all just history. And I want to illustrate the extraordinary properties of entangled states. I will not illustrate this with the example that the EPR considered, but I want to illustrate it with the entanglement of three particles. And the example is known as the GHZ game, or the Grimberger-Horn-Zeilinger game. It really illustrates the fact that in quantum mechanics, the notion of reality is flighty. Is this a word?
Flaky.
It's hamakmak. Okay, so let me describe, it's a game. Let me describe the game. So it's a game where Alice, Bob, and Charlie play against the house. So they have to develop some strategy so that they would win over the house. And let me explain now what are the rules of the game. They will be asked one of four questions: question 1, question 2, question 3, or question 4. Question 1 would be to pose to Alice the question X, to Bob the question X, also question X, and to Charlie the question X. Now, if Alice is being asked the question X, the legitimate answer to the question X would be either +1 or -1. And Alice, Bob, and Charlie would win this round if they were asked question 1, if the product of the responses is -1. Now, they might also be asked a different question, which is question 2, where Alice is being asked the question Y, Bob the question Y, and Charlie the question X. And in this case, they win if the product of their answers is +1. Question 3 is when Alice is asked question X, Bob Y, and Charlie Y. And question 4 is when Alice is Y, Bob is X, and Charlie is Y. And now the question is, can they develop a strategy where no matter what question they are being asked, they win? And the answer is no. And it's very easy to see that you can't win this game always. Let me describe a strategy that would win it most of the time. So for example, they decide that no matter what question we are asked, we answer plus. So if they answer plus, no matter what question they are asked, they win question 2, they win question 3, they win question 4, but they lose on question 1. So they win on 75% of the questions. Now you can ask yourself the question, is there a better strategy? There isn't. There is no way to fill this table so that it is satisfied. And the proof is very, very easy, simple. The way to see that there is no way to fill this table is the following. Look at the column of Alice. You see that the question X is being asked twice. So no matter if Alice picks the answer plus or minus for X, the product of these two XA and XA in the question for question 1 and question 3 gives plus. The question Y is also being asked twice, so no matter what she picks, the product of the answers is Y. Therefore, the product of the first column is +1. Similarly, the product of the column on the second column is +1, and the product of the column of the third column is also +1. Therefore, the product of all the entries in this table is plus. However, if you look at the product of the rows, it's -1 here, +1 here, +1 here, +1 here. So the product of all the entries is -1 if you want to win all the time. Moral, you can't fill this. It's impossible to fill this table so that it is always satisfied. You cannot fill it with numbers because the multiplication of numbers is commutative. But you can fulfill it with matrices. This is what, so the miracle of quantum mechanics is that if Alice and Bob share a quantum state, which is written here, it's an entangled state, Alice, Bob, and Charlie, Alice, Bob, and Charlie, where it's an entangled state of 0, 0, 0, minus 1, 1, 1. It turns out that if they share this entangled state, and they are being asked, no matter what question they are being asked, they can give an answer that would satisfy this table, and the way they do it like this. If Alice is being asked the question X, she measures X, the operator, the Pauli matrix X on this GHZ state. If she's being asked the question Y, she measures Pauli Y operator. Now, it turns out to be the following is true, that no matter what question you are being asked, this state always satisfies this table. So what does it mean? It means that quantum mechanics doesn't try to fill all the entries in the table. It only fills one row, the row which is being asked. If you ask a different question, you get different answers. But the answers always have the property that they satisfy this table exactly. I think this really shows that quantum mechanics' notion of reality is weird. It depends, what reality is depends on the question you're being asked. I don't know if I got this through or not, but okay. It is basically, well, since you could teach it to your students in quantum mechanics, Asa, you could do this. It is basically based on the fact that the question 1 is represented by the product of 3 Pauli operators X, and the question 4 is 2 Y's and 1 X. And you can check that all 4 questions commute. Right, the 4 questions commute. This means that one can find a state which would satisfy these questions. I'm not sure I made this very, very clear.
Yosi, this is also used to argue the no hidden variables, right? I mean, there's no way you can add degrees of freedom to make this work.
That's right, yes. This really shows, well, thank you. And now I started this lecture by telling us how blue sky research, how useless knowledge eventually can become useful. And I want to mention that an interesting development that happened, what was this? 50 years after the EPR paper was the work of David Gershoni and Nathaniel Linder in this department, where David Gershoni found in his lab, they found a way to manufacture entangled states in what is being called on demand. So you press a button and you get an entangled pair. You press the button, you get an entangled pair. And as I mentioned, this is technologically important. And the entangled pair are basically created by the fact that you have a 4-level system. If the system starts at the top state, it can decay by first emitting a red photon and then a blue photon through this path. And then the polarization, say, is 0 of the both photons. But it can also go through this path where, again, first photon is red, the second photon is blue, but then the polarization is different, is a different photon. Since quantum mechanics does not make choices, it follows both paths simultaneously. And this is why the state after the decay of the excited state leads to this entangled photon pairs. So this was one thing that I think was a nice consequence of entanglement. And I mentioned another important consequence of entanglement, which is again related to what happened to our department, that in 1993, Asher Perez, who, as I mentioned, was a student of Nathan Rosen, and 6 other authors, which are shown in this picture, Charlie Bennett, Gilles Brassard, Crépeau, Josa, and Perez, published a paper where they introduced the notion of quantum teleportation. I don't think I have enough time. How am I with time, by the way? I should have stopped half an hour ago.
I don't think so. No, you're just fine.
Whatever that means. I don't think I have enough time to explain the teleportation, which is a delightful thing in quantum mechanics, but I'll tell you one nice story that I heard. When the teleportation paper came out, the reporter interviewed Asher Perez and asked him something like this. Well, now it's nice, you physicists know how to teleport the body. When would you know how to teleport the soul? To which Asher Perez said, you are completely wrong. We teleport only the soul, not the body. The point, do you see the point? In teleportation, no particles move from here to there. Alice's particles stay with Alice, Bob's particles stay with Bob. The only thing that moves is the wave function. The wave function that originally sat on Alice's particle is now sitting with Bob. So it's only the information of the soul of the particle, but the particle doesn't move. And I think this brings me to the end of the life story of Nathan Rosen, who died in December 1995. And thank you.
Thank you very much, Yosi. So we questions from the audience. Joshua?
Is it known who was the referee for CEPR?
I don't.
You might have said it and I missed it, but where did he go to school? Where did he do his undergraduate? And
MIT.
is our Podolsky related to the other Podolsky?
Unfortunately not. He was, by the way, Podolsky was a professor at USC after that. He was apparently a very gifted guy.
I heard he was a professor at the University of Cincinnati, but the department was so bad that he transferred to Xavier.
To what?
He transferred in Cincinnati to a Catholic university, and for that he had to convert to Catholicism to go to a better physics department.
Okay.
More questions from the audience. We have an online question from Adi, but I'm not sure how to.
Yeah, I unmuted. You can ask.
Okay, Adi, you can ask.
Yosi, hi, very nice talk. Can you hear me?
Yosi, can you hear him?
Yeah, faintly, yes.
Yeah, I was wondering how much of Einstein's views did Nathan Rosen hold regarding quantum mechanics in general?
Can someone tell me what the question was? I don't know, from which loudspeaker does it come? It comes from some strange loudspeaker that we don't know where it is.
Just a moment.
I'll write it in a chat.
Okay, perhaps now it will be better. Can you ask again?
How
Please?
much of Einstein's views did Nathan Rosen accept in regard to quantum mechanics and God plates and things, dice and things like that? How much of Einstein's views did he accept regarding?
Whom? Nathan Rosen?
Yes.
It's a tough question, and I don't know if I'm qualified to answer. Perhaps Joe Rosen, who is, I think, in the audience, could say better. I would say, I can't say about quantum mechanics, but I will say something about general relativity. So I'm not answering the question you posed, and I'll answer a different question. You see, Einstein had an objection. In this Einstein-Rosen paper, they say very explicitly what they don't like about the Schwarzschild solution. And what they don't like about Schwarzschild solution was the singularity, because, as they say in this paper, because once you get the singularity, physics, the uniqueness of physics get lost. There are just too many possibilities to continue from there. So I think this reflects perhaps Einstein's view that Einstein was a Spinozist, you know, he really was a determinist. He liked determinism. So, and the fact that, for example, quantum mechanics allowed too many random possibilities he didn't like, and for the same reason that the singularity in general relativity, he didn't like it, again, because it offered the scene for too many possibilities of how do you make an extension from the singularity. And I think this view of Einstein, I don't know if I should use the word haunted, or was a guideline principle for much of the research that Nathan Rosen did in general relativity, because he tried to reformulate general relativity in such a way that it will be free from singularities. And among the theories he advocated or advanced was a theory that he called the bimetric theory of relativity, with the two metrics that worked together in order to avoid this singularity. So I didn't answer the question on quantum mechanics, but I think there is definitely no question that Nathan Rosen was heavily influenced by Einstein. By the way, they continued with closed friendship all through the years. There is a stack of personal letters written between that Einstein wrote to Nathan Rosen, which the family owns, and in fact, I think there was a warm and steady friendship between the two men all their lives, and they corresponded in German.
We have a question by Oren Bergman also. Oren?
Thank you for a very nice lecture. Thank you for a very nice lecture.
Thank you.
I wanted to mention a different story. Other than
אתה
a
מקוטע. אני לא יודע איך אומרים אתה מקוטע באנגלית.
Rosen's second great achievement is the Einstein-Rosen bridge. A few years ago, Podolsky and proposed that these two things are related, namely that any pair of entanglement particles are actually connected by a wormhole, suggesting a deep connection between quantum mechanics and general relativity. And they even wrote down in a music ER equals ER.
Yeah, thank you. You were heard very, how would you say? You were not, the connection was not very, very good, but I appreciate and I thank you for this remark. I also know that our good friend from Stanford advocated this, making this EPR to PR connection, and I appreciate that. Yeah, that was an important result because it makes impact even today. Thank you, Oren.
And the last question by Guy Fetzroni.
Yeah, okay. I know Guy Fetzroni. Good.
Hi, Yosi. Thank you for the interesting talk. So I want to ask if you can say something more about the Rosen's contribution to the PR paper. Sometimes in the papers of this paper, is different from other people blame Podolsky, and the contribution of Rosen is sometimes people don't talk about it, or it's not maybe clear historically what it is.
One particle quantum mechanics looks just too similar to wave mechanics. But when you look at two particles, quantum mechanics appears with all its glory. And I think since Nathan Rosen, during his PhD, worked on a problem involving more than one body, on many body problems. He did, for example, among other things, he did the problem of H2. And so he looked at problems with more than one particle, and I imagine that the fact that one should focus on many particle wave function was his contribution, but I wasn't there either.
Why did they speak in German? He was an American.
Who? Nathan Rosen, yes. But I would guess educated American in the 30s, especially physicists, had to know German.
He probably descended from a German family too.
No, he was Russian. The family was from Russia. Yeah, they escaped pogroms in Russia.
Well, thank you, Yosi, for the great talk. Thank you all.